Hello, calculus students. This video is looking at classwork we had from a couple weeks ago before our exam. Some of you remember that I was trying to teach from my office, and unfortunately I had forgotten my pen, and so I wasn't able to do these problems completely. I know that some of you have seen Riemann sums before, maybe if you had calculus in high school, but I wanted to make sure to go through a couple of examples for those that haven't seen it. The problems are actually quite straightforward, but I just wanted to be able to give you a visual to show you what was going on behind the math. So a Riemann sum is a set of rectangles that we're adding together to estimate the area underneath a curve. And we have different ways that we can calculate that area. The difference comes from what we choose to be the height of each rectangle. One of the things that we're going to do for all of these problems, however, is we'll have the base of the rectangles be the same length. So looking at number 1a, for number 1, we're looking at the distance between 0 and 10 from some function that we don't know. We don't know necessarily what this function is. We can see it there in red. Number A is telling us to set up 5 different rectangles. So since we will want those to be the same distance from one another, we will have the bases of each of those be a length of 2. So I'm just kind of drawing where our the bases are going to, our breakpoints. The rectangles are going to be determined by the right endpoint. So that's going to be from the right-hand side. I want a highlighter. There we go. I want to grab the right-hand side of each rectangle to be the height of the rectangle. So the right-hand endpoints are going to be at 2, 4, 6, 8, and 10. So this first rectangle, the height is going to be up where the rectangle meets the curve. So here, looking at when x is equal to 4, it looks like the height is equal to 3. At 6, it looks like we're going up to maybe 3.5. So I'm just drawing the rectangles that we're going to be summing up here. Okay. So our total, I'm going to call that capital R for the Riemann sum. And it's going to be a rectangle, I'll call this R sub 1 plus R sub 2. I'm just using lowercase to denote the 5 different rectangles. Now the base of each of them is 2, as we saw. So we'll set this up as like this. R sub 1 plus R sub 2. So here's my 5 rectangles. They're all going to have 2 as the base. And then they're going to be, actually, I don't want those parentheses because what we're going to do is I'm going to multiply by f of 2. What I'm saying is I'm looking at 2, which is the right-hand side, and I want to know what the value of when I plug x into the function, and f of 4, f of 6, f of 8, and f of 10. So that's what I'm going to use for my estimate. Now, as we move forward, you'll notice that what we'll probably do is each of the bases are the same, so maybe we could factor that out to the front and just add up the function values. So I'll do that. I'm going to bring a 2 out to the front, and what I'm doing is I'm taking f of 2 plus f of 4. This is just maybe a faster way to kind of calculate what we're looking at. So I'm going to just kind of rough estimates of what the values are. When x is equal to 2, it looks like the function value is maybe about 2.4. So I'll put that here. When x is equal to 4, we said that the output value looked like it was about 3. When x is equal to 6, the output value is about 3.5, just a rough estimate here. And then when x is equal to 8, it looks like the output value is maybe 3.75. And then when x is equal to 10, looks like we're a little bit above 4, maybe 4.2. This is not an exact science here. So let me just grab a calculator. 2 times 16.85. And so I think that my area is approximately 33.7 square units. All right. Letter B is the same exact type of problem. The difference here, though, is that we're going to use the left endpoints rather than the right endpoints. So let's go back and erase everything that we have up here. We're still having 5 rectangles. Yeah, we're still going to have 5 rectangles. Oh, we didn't answer one of the questions above. Based on what we're doing for part A, this is going to be an overestimate because the rectangles that we drew were above the curve, right? So this is an overestimate. Just go back for a second. What I mean by that is the original rectangles that I drew were here, and I can see that this part that's being calculated in the rectangle is actually more than what's underneath, than the area underneath the curve. And so I've got these extra spaces in my total estimate. And so we're anticipating that that value is actually greater than the actual value for this particular curve. It's going to vary from curve to curve depending on whether they are increasing or decreasing. So this is what we did for part A. For part B, we're going to use the same bases, but now we're going to use the left-hand side for the height of the rectangles. Still at 2, 4, 6, and 8, but now 0 will be one of the heights that we consider. And notice that our rectangle on the far left, I'm going to call this guy R sub 1, the height of it is 0 because the function value at 0 is at 0. And when we plug in x equals 0, we get y equals 0. R sub 2 is here, R sub 3, R sub 4, and R sub 5. And again, the heights are coming from these points on the left-hand side instead. So let's do another calculation. For this estimate, we'll have, again, our base is going to still be 2 for all of those. And then I'm going to add up the function values at 0, 2, 4, 6, and 8. So some of the ones I have from above can be the same. I had 2.4 here, 3, 3.5, and 3.75. I'm just using those same values that I had up here above. But then we saw that when we plug 0 into the function, we actually get 0 here. All right, so let's plug that into a calculator. And I'm getting 2 times 12.65, which is 25.3 square units. And this is an underestimate. We know that because there are, well, first of all, this very first rectangle, we're not including any of that part under the curve. We're also not getting this part, this part, this part. There's space under the curve that we're not calculating in this calculation. The third example, the third problem, number C, letter C, is having us look at the midpoints of each of those rectangles. And so we're hoping that maybe that's going to be a better estimate because maybe it's going to split the difference of the over and the under estimate. Let's do that one. All right, going back up here. Everything's going to be the same, but what we're changing is the heights. We're still having 5 rectangles, so the breakpoints are still going to be at 2, 4, 6, 8. But our heights now are going to come from the middle, which is going to be at 1, 3, 5, 7, and 9. So here's rectangle 1. Rectangle 2 is here. Here's the third one. Ours are 4. And then the 5th. All right. So for this one, our Riemann sum is going to still be 2 for all of the bases. We'll do f of 1 plus f of 3, f of 5. Again, these are all the heights. F of 7 and f of 9. Okay, so let's see what we have. About 2 and 2.75. I think this one's 2 and this one's 2.75. F of 5 is at maybe 3.25 and maybe 3.6. I'm just kind of estimating. And then f of 9, maybe at 4. Okay. All right, let's plug that into a calculator. Getting 15.6. So for my estimate here, 31.2 square units. Now, the overestimate that we had was 33.7. The underestimate that we had was 25.3. And so looking at this, it kind of makes sense, this answer that we're getting with using the midpoints, because it's in between the two and it's maybe splitting the difference. So that's a better process to use the midpoints. An even better process would be to use more rectangles, right? So rather than just having 5, what if I had 10? If I had 10 rectangles, and I'm using the midpoint for all of these, that I'm going to draw. I'm taking the midpoint like in between 1 and 2, and 2 and 3, and here the midpoint in between 3 and 4. So I can see that the more rectangles I have, the better that estimate is, because I'm getting closer and closer to the actual function. And so what we'll be working towards this week is taking the limit as this base value goes to 0 and adding all of those smaller and smaller rectangles together. The idea being that if I were eventually getting really, really skinny rectangles, they would all be, lined up next to each other, and it would fill in the entire space. And so that's how we're going to move towards finding what we call the integral. All right, I'm going to pause here and then I'll start for the next problem in just a moment.